Okay, so today's video we're going to finish talking about Newton's laws and do some application problems to help apply forces to physical situations. So we already talked about first and second law, so let's quickly recap that. So remember, first law, okay, is essentially identifying what a force does to an object, right? It says if there is a net force, then the motion of the object changes. Okay, so remember, that basically means if an object's at rest, it'll stay that way, and if an object's moving in a straight line at a constant speed, it'll continue doing that unless there's a net force that acts on it. Okay, so and it's important to say that when there is a net force, that means when we calculate the total forces of all the objects, it does not equal zero. That's what we mean by saying that there is a net force. Okay, so second law, okay, told us that when we're looking to calculate net force, okay, it turns out that the acceleration experienced by an object, so acceleration A, was proportional to the net force divided by the mass. Okay, sorry, rather, it's proportional to the net force, but inversely proportional to the mass. Okay, and we typically will use this in application form as saying the net force, or rather the total force, results in changing the motion of a mass, or rather mass times the acceleration. And also remember that these numbers are vectors, so they do have direction and magnitude. Okay, and so before I finish this with Newton's final third law, I want to emphasize a little bit more on what we exactly mean by net force. So let's say we have an object of some mass. We'll say the mass is, I don't know, say 10 kilograms. Okay, and we apply a force in multiple directions. Okay, so we've got a force to the right, and we'll say that that is 15 newtons, and we have a force to the left of, say, 12 newtons. Okay, so what we want to know from this is what is the acceleration of this object. Okay, so if we're trying to figure out how much the motion's changing, the acceleration, then Newton's law tells us, second law, that the net force is equal to mass times acceleration. So we got to break this into two parts. Before we can just, don't know mass, we know the mass, but we don't know the acceleration. So we can't just calculate net force using m times a. However, remember that net is a way of saying total. So we could calculate the total force acting on this object. So let's start there. So in our picture, we had 15 newtons, which is a positive 15 newtons because it's going in the positive direction. Okay, so to the left would be negative. That means that what we're essentially doing, because net force means total, so we're adding together numbers, but the 12 newtons is a negative number. So we're doing a positive 15 newtons plus a negative 12 newtons. Okay, and that's equal to the mass times the acceleration. Now the mass we already had was 10 kilograms, and we didn't know the acceleration. That is what we're looking for. So when we combine the forces on the left side, 15 newtons plus a negative 12 gives us a total of 3 newtons. So that is our net force. And now we need to solve it for a, so we get the acceleration is 0.3 meters per second squared. Okay, and a quick note on units, because you might be wondering where these units are coming from. Well, if we focus on Newton's second law, that net force is ma, Okay, let's look at this in terms of units. Well, what are the units on the right side? For mass, you have kilograms. For acceleration, you have meters per second squared. Okay, so when I multiply those together, nothing cancels and nothing changes because these three things are different. Kilograms is a mass, m is a meter for distance, and seconds, s is for time. So these are three different physical quantities. So none of them cancel, none of them do anything spectacular. So it just becomes kilogram meters per second squared. And that represents our unit of force. And what we've done is, rather than constantly saying kilogram meter per second squared, we termed it after the person who identified the laws of forces and called it a Newton. So a Newton is made up of a kilogram meter per second squared. So if you want to check those units here, that's exactly what we did. We took a Newton and we divided off a kilogram. So if I look at what makes a Newton, and we take away the kilogram by dividing it out, we're left with the unit for acceleration. So that confirms that what we did was right. Okay, and so that's the basis of using Newton's second law. Now we could have, instead of saying 15 newtons and 12 newtons, we could have given those names like tension or friction and gravity and normal force. I mean, we could have given them names, but it doesn't change how we solve the problem. All right, so let's talk about third law. Okay, so Newton's third law talks about the interaction of objects and the forces between them. Okay, so in an elementary class, because most students remember this, they heard Newton's third law as saying every action has an equal and opposite reaction. Okay, so that is essentially Newton's third law, but it needs a little refinement if we're going to try to really understand what it's doing. So here's the idea. Let's say I've got two objects, whatever they might be, say object A and object B. Okay, now you'll notice that these two objects are touching. Okay, so this part where they're touching, this is where Newton's third law is happening. In other words, there's no forces on the outside. It's not about, if I'm pushing a force here, or a force here, or a force here, or a force here. It doesn't matter. None of those matter. What matters is what's going on in the interaction of these two objects. Okay, so let's take this picture and blow it up with just focusing on the interaction. Okay, so if we're looking at where these two objects are touching, if you were object A, for example, and you were touching object B, you would feel a force from B pushing on you. So this is a force from B. If you were object B, you would feel a force pushing on you from A. Okay, so you feel these two forces going on between you. Now, the important thing to understand is nothing is changing about the shape of the boxes, which means neither force is causing a box to deform or change shape or doing anything. And therefore, what that means is that internal forces always cancel each other because they're not having any effect on the net motion of the object. So internal forces cancel one another. And that's essentially what Newton's third law tells us. Okay, that the force from A is equal to, but opposite in direction, to force on B. In fact, that's exactly what we said. Every action has an equal and opposite reaction. So the two F's are the same, but they're in opposite directions. Okay, so here's why that would, or how that would apply to physics. So imagine you've got, say, we're in outer space, and you've got two astronauts. So you got astronaut 1, who has a mass of, we'll say, 80 kilograms. But then you have another astronaut, say astronaut 2, who's a lot smaller, at a mass of, say, it's unrealistic, let's say 60 kilograms. Okay, now what would happen if the two of these astronauts pushed on one another? So imagine they take their hands and they put their hands up against one another and they both push. So the question is, who pushes with more force? Now, it should be easy to guess that the larger astronaut pushes with more force, because the smaller astronaut, because they're smaller in mass, they're going to fly away at a much larger velocity than the larger one. So we could say, well, the larger person must have pushed with more force. But Newton's third law tells us that that is just not true. So how is it that the little astronaut moves away at a greater rate than the larger one? And the answer is, well, each astronaut, so let's label 1A and 1B, they each push on each other with equal but opposite forces. Okay? And if that's the case, then we can write this out as, well, each force, because of Newton's second law, is a mass times an acceleration. Okay? Now, and let's label these further. So this is the mass of A and his acceleration, and the mass of B and his acceleration. Okay, so each of these is Newton's second law. There's a negative sign. Now, if we were to calculate out what's going on with the accelerations, well, mass A is 80 kilograms. Mass B is 60 kilograms. Okay, and while we do not have either acceleration, what we can do is look at the ratio of these two things. In other words, if I divide the 60 over to the left side, and I divide astronaut A's acceleration to the right side, and I work this out, I find that astronaut B will have roughly 1.3 times more acceleration and in the opposite direction than astronaut A, which is what we said when we noticed the smaller astronaut moves away at a greater rate, because his acceleration is bigger. And his acceleration is bigger because his mass was smaller. Okay? The way to think about it is, if I have to keep my force constant, which it is, it's constant between the two people, okay, then the product of that force is mass times acceleration. Well, if I'm trying to keep F the same, but I make the M really big, then that means the acceleration has to be very small, which was the case for astronaut A. Now, same amount of force, but this time I make the mass really small. What happens to the acceleration so that the overall product is still the same force? They must have a larger acceleration. Okay? And this is true for every single thing. Every interaction has an equal and opposite reaction. So let's try another example. In this example, we have the Earth. And then you are standing on the surface of the Earth. Okay, now if we want to know the mass, well, the mass of the Earth is really big. Mass of Earth. And the mass of you is very small. Okay, so if you were to suddenly jump in the air, okay, so let's say instead of drawing you here at the surface, we'll draw you up a little bit. So we're going to say you jumped a little bit, and you've got a tiny little mass. So we know that the force that pulls you back down is a force due to gravity. Okay, but because of Newton's law, it turns out that you pull up on the Earth with the exact same amount, but in the opposite direction. Now, how can that possibly be the case? The Earth doesn't move. And the answer is, well, it does, but it's so small that there's no way we would ever be able to measure it. So again, if we do this idea where we apply the same amount of force, now it's opposite directions, but let's just talk magnitudes here. The strengths of the force is the exact same. But for the person, so we'll say this is the force from Earth, and this is the force on the person. The force on the person has a very tiny mass, whereas the Earth has a very large mass. So what does that mean about the respective accelerations if I want the forces to be the same? That means the acceleration the Earth feels is very small. But the acceleration that you feel is very large, which is why you notice when you jump in the air, you get pulled back pretty quickly. You actually get pulled back at exactly 9.8 newtons per kilogram of mass that you have. Okay, and the Earth ends up moving up by a very tiny amount, but it's so small that there's no way you would ever be able to measure it. And that is the idea of Newton's third law.